With the development of AI technology and the high demand for AI edge devices, low-power, high-energy efficient computing chips are highly valued by the industry. Deep neural network is currently applied to various artificial intelligence tasks including computer vision, speech recognition, drones and robotics. Visual signal processing is a crucial aspect of artificial intelligence. Although deep neural network provides very high accuracy to process visual information, the massive model causes extremely high computing power consumption and is difficult to implement in mobile devices. This project aims to solve this crucial problem by integrating biological principle and neuromorphic architecture with deep neural network to develop a neuromorphic intelligent visual system on chip for mobile devices. By integrating the four features, including low-power intelligent visual image sensor, low-power and low-latency deep learning chip based on neuromorphic intelligence, vision-based neuromorphic obstacle avoidance algorithm, analog-digital integrated AI chips and architecture. We aim to design, develop, and integrate a low-voltage, low-power, real-time mobile neuromorphic intelligent visual system that can perform tasks of recognition and track prediction. This project's principal investigator is Professor Kea-Tiong Tang, who leads and coordinates the research. Subproject 1 principal investigator is Professor Chi Cheng She, whose team is responsible for developing the low-power intelligent CMOS image sensor. Subproject 2 principal investigators, Professor Kea-Tiong Tang and Professor Herming Chue, co-developed the low-power and low-latency deep learning chip based on neuromorphic intelligence. Subproject 3 principal investigator is Professor Chung Chuan Lo, whose team is responsible for developing the vision-based neuromorphic obstacle avoidance algorithm. Subproject 4 principal investigator is Professor Ren Shuo Lu, whose team aims at developing analog-digital integrated AI chips and architecture. Inspired by the fruit fly, a neuromorphic intelligent visual system on chip is developed for obstacle avoidance. The chip enables the drone to dodge obstacles like the fruit fly with low power consumption. To accomplish this, the first thing is to solve the problem of massive data transmission.
原先的处理的影像是整只手的影像，但是呢，如果我们使用这个 Edge Mode 的话呢，我们就可以只传送只有边缘的影像。 这个影像的数据量就会大幅的降低。
我现在可以用手势去操控这台无人机，然后像我这样比5的话，就是前进；那0的话呢，就是后退。
Optical flow is the images formed on the retina when we observe moving objects, just like the flow of light.
我们的神经网络来侦测光流，所以光的流动就是相机在移动的时候可以看到景物的。 变化，那可以借由摄到相机本身移动的方向，前进、左右或上下。那这神经元就组成一个好像电路的样子。那我们借由研究这个神经网络的结构，那我们可以猜测出来说它这个功能到底是怎么运作的。那我们利用这个功能，这运作的原理来设计我们的仿神经晶片。
This year we have several breakthrough technologies. And we are integrating them to develop a low-voltage, low-power, real-time, neuromorphic intelligent vision system for object identification and trajectory prediction. The frame difference image sensor achieves low power and real-time motion detection capabilities, which is suitable for the applications of mobile devices and drones. In this demo system, the control signals and data output of the frame difference image sensor are interfaced through the FPGA with the programmability of exposure time, operating frequency, and imaging resolution. Unlike traditional cameras, the frame difference image sensor we developed will only detect the moving image part. Therefore, for the image sensor, the dot in the middle is not rotating, only the rotating circle next to it can be seen. The screenplay shows the motion detection result of the sensor, which contains black, white, and gray parts. The black and white pixels represent the leading edge and lagging edge of the moving direction of the object, respectively, while the gray pixels represent no object moving in the area. When the screenplay is paused, the motion information with leading and lagging edges can be seen clearly. Neuromorphic optical flow distance estimation. Imitating the Drosophila nervous system as the conceptual basis to integrate image information, motion detection, and the resulting distance estimation algorithm. This algorithm is programming on Raspberry Pi to capture the video from the computer and then calculate it for Raspberry Pi. The video on the left side is the raw image, and the right side is the result of depth detection. The red color means closer, and the purple means farther. This is a digital SNN chip. We implemented the SNN chip on the FPGA. We used the SNN chip to solve 4x4 Sudoku. You can see that there are 1 to 16, representing 16 positions from the upper left corner to the lower right corner, and 1 to 4 represent which number each position is. We used 64 neurons to realize the function of solving Sudoku. This is the CIM chip. We implemented the RTL code into the FPGA for image recognition. We chose CIFAR10 for image recognition. The picture on the left side is what we want to recognize. We used the left and right buttons to select the picture. For example, we chose an image as a cat, then pressed enter. The result is shown on the screen. Another application is to detect moving object in the image. We caught the moving object by the camera, and the image of the object was sent to the CIM-based chip for computation. The result is shown on the screen. Tiny YOLO version 2 real-time object detection system can highlight the objects needed in the video. We use Synopsys HAPS 80 FPGA as the verification environment. The clock rate of this FPGA is 42.5 MHz, and the detection rate of the video can reach 3.91 frame per second. Emulating to the chip frequency of 400 MHz, the detection rate can reach 36.8 frame per second, which meets real-time requirements. In order to integrate aforementioned SIS and CIM technologies with a UAV, we must master the UAV's core CPU and UAV's know-how. We have integrated a Synopsys ARC CPU and open-source and in-house algorithms to design a UAV flight control system. More specifically, we use an ARC development board with a self-developed daughter board to connect to an IMU sensor, altitude sensors, motors, and buttons. We can maneuver our UAV to pitch down, pitch up, roll left, roll right, rotate counterclockwise, and rotate clockwise. And we also can lift the UAV and again maneuver it to pitch down, pitch up, roll left, roll right, rotate counterclockwise, and rotate clockwise. The technologies developed by this project can be applied not only to drones, but also to smart agriculture, smart home, robotics, etc., to create high values and better life environment.